In this topic, we turn our focus to determining the domain of a function when that function is written as an equation. Let's begin by recalling our basic definitions. The domain of a function is the set of all x values in the function. The range of a function is the set of all y values in the function. So when we are focusing on the domain of our functions, we are going to be focusing on the set of all possible x values that make the function true. Now let's recall some notation. Remember, when one dependent quantity is a function of another independent quantity, like when we have y as a function of x, then the dependent quantity will usually be renamed f of x, which we write mathematically as f with the parentheses and x inside. For example, when you see the equation y equals 3x squared plus y, this equation defines y as a function of x. Now, using function notation, we could rename the y as the quantity f of x, and then our equation would look like f of x equals 3x squared plus 1. All of the equations in this topic are going to be written in functional notation, so it's important that you're familiar with it. Now, the main principle in this topic will be determining the domain of a function f of x. How do we go about doing that? Well, first we're going to consider the function as it's written as an algebraic equation of x. Then we're going to look for any x values that would make the function undefined. Now, in general, most functions that we encounter in algebra have a domain of all real numbers. In other words, there is no restriction on the x values that can be used in the function. For example, let's take a basic linear function. F of x equals negative 1/2 x plus 7. When we look at this function here, we can put any number we want in place of x, multiply it by negative 1/2, add 7, and wind up with a numerical value. This means that the domain for this function is all real numbers. Likewise, if we were to take a look at one of the quadratic functions, because we've talked about quadratic equations, but if we take a look at a quadratic function like 3x squared minus 2x plus 8, again, notice that we can plug fractions, negative numbers, positive numbers. We can plug anything in for x and get back a real value answer as the range. Because no matter what input we put in, we get a real number output, again, we would say that the domain of this function is all real numbers. Now, there are two functions that we have to be careful of. Those are the functions that we're going to focus on in this topic. Rational functions and square root functions are functions that both have restrictions on their domains. What am I talking about? Suppose I have the function r of x equals 3x over x squared minus 8x minus 20. A rational function, recall, is a polynomial divided by a polynomial, a ratio of two polynomial functions. And in rational functions, there is something that we have to be careful of. Remember, the denominator of a fraction cannot be 0, right? Anytime the denominator of a fraction is 0, that whole expression is undefined. So in rational functions, we are going to have to be careful and determine what x values would make our denominators equal to 0. Those values are not in the domain of rational functions. Similarly, in a square root function, let's say, for instance, the square root of x minus 11 plus 7x, this would be a square root function, a function that involves a square root. Again, we have to be very careful about the values that we plug into this function. Now 7x, this we could plug anything into. However, we know that when you have a square root, the value or the number, or if you like the argument under that square root, must always be either positive or 0, right? You cannot have a negative number underneath a square root. And because of that, that will lead to restrictions on the domain for this type of a function. So to summarize, we are going to focus in this topic on looking at the domains of rational functions and square root functions and determining how to find those domains for those particular types of functions. This brings us to our main idea: how to determine the domain of certain types of functions. We start with the domain of a rational function. To determine the domain of a rational function, we want to find all x values that make the rational function undefined. In other words, we will look for all the x values that will make our denominator equal to 0. Note that often, to find where the denominator equals 0, we will first have to factor the polynomial that's in the denominator, and then use the zero factor property to solve. Once we find these x values that make the denominator equal to 0, we will disregard those values from our domain. For instance, let's take the rational function p of x equal 7 divided by 4x squared minus 9. When we're looking at the domain of a function, we are asking the question, what x values can we substitute into this equation and come out with a true real number as the result? Our first step in determining what values we can plug into this equation or function would be to first of all look and determine what values would make my denominator equal to 0. We don't want the denominator of a fraction to be equal to 0, because if it is, then the whole expression is undefined. And how do we solve a quadratic equation? Well, we begin by factoring, right? So the key here is we want to factor that denominator. This is a difference of squares, do you see? 4 is a perfect square and 9 is a perfect square. So this factors as 2x minus 3 times 2x plus 3. Now, where does 2x minus 3 times 2x plus 3 equal 0? Well, it will be 0 where both of those are equal to 0. So let's set each of those individual factors equal to 0 and solve. That means that x could not be 3/2, or x could not be negative 3/2. Because if it was, then that would make the expression undefined. We do not want x to be 3/2, and we do not want it to be negative 3/2. Because if it was 3/2 or negative 3/2, that would be where our denominator is equal to 0. These are called the restrictions on our domain right here. We call these our restrictions on our domain. Let's take a look now at the domain of a square root function. To determine the domain of a square root function, we want to find all x values that will make the square root function defined. That is, a real number. In other words, we want to determine all x values that make the argument of the square root function non-negative. Note that often to determine where the argument of a square root function is non-negative is actually saying where is that argument positive or 0. Thus, we'll have to solve the inequality argument greater than or equal to 0. For instance, suppose I have the function s of x equals the square root of x plus 5. This is an example of a square root function. Now, to determine the domain of this square root function, we want to focus on what values we can plug into this function so that the object that's underneath is not a negative number. Well, how would we do that? We would want to focus here and make sure that all these values are greater than or equal to 0. So we would create an inequality. We would say that our argument x plus 5 must be greater than or equal to 0 for this to be a real number answer, a real number result. And then we would go about solving that linear inequality. Recall, we solve linear inequalities very much like linear equations, except a few rules when negatives are concerned, which we'll get to in our examples later on. For now, we see that for this particular square root function, x must be greater than or equal to negative 5. We say that this is the domain restriction on this particular function. So let's take a look at several rational functions and square root functions, and let's determine the domain for each of them.